You're listening to MedX, the Medical Extrusion Podcast, presented by U.S. Extruders. Extrude with confidence. Custom extrusion equipment designed for you and your application.
Hey folks, welcome back to the MedX Podcast. Today's discussion is focused on custom stent and frame covering, and our guest is Chris Steadham, the General Manager at Medical Murray based in Charlotte, North Carolina. Medical Murray is a contract design and development manufacturing organization focused on minimally invasive devices and implants. Enjoy. Hey, Chris, thanks for taking some time to join us on the podcast today.
Oh, my pleasure. My pleasure.
Great. I'm really excited about this conversation. I wanted to ask to kind of get as an introduction to learn about covered stents and, why are stent frames covered in the first place? Why not bare metal stents?
Well, covering offers you the ability to protect areas. Maybe there's an aneurysm, maybe there's a dissection. There could be some other medical reasons to do it. But they've been around for many years and are becoming more popular now. But those are some of the traditional reasons.
Okay. What are, just kind of an overview again, some of the capabilities that Medical Murray has related to covering stents with expanded PTFE or coatings or laminates?
Yeah, so most of this type of work occurs in our Charlotte facility, and we use ePTFE membrane. We can use ePTFE tubing. We can use composite systems that either we bring in composite material or we create the composites ourselves. And then we can also dip coat frames with other elastomeric materials.
Okay. Yeah, we'll get into that a little bit later when we talk about composites. When I look at stents and covered stents, they're usually in a tubular form, but often I see kind of unique shapes, right? Bifurcations, maybe a taper on the distal or a flare. Talk a little bit about some of these unique geometries.
Yeah, so, in the AAA, traditionally, your covered stents were just tubular. They would that into a coronary or peripheral vascular area, and it would be a straight tube, maybe 100 millimeters, 200 millimeters with a simple covering. As more and more ePTFE is becoming used, people are wanting to put in the different locations. You mentioned a bifurcation. It could be up in the aortic arch, some of the structural heart work. ePTFE is a great material because it's so inert in the body. And you can control the porosity of the material that will allow for ingrowth. You can exclude ingrowth. There's a lot of things you can do with the material that makes it a good choice for many applications. And engineers and physicians are really creative in coming up with these shapes to put them in different areas. It could be left atrial appendages, something as simple as a taper to better conform to some of the anatomy. These are all things that are that we're seeing.
Okay. In some applications, the expanded PTFE is in a tubular form, and other times it's in a membrane. When would you use one over the other from an application standpoint?
Yeah, that's a great question. The membrane allows us to customize properties to very specific areas within a given structure. It also allows us to work with very asymmetrical or complex geometries where the tubes kind of lock you into some of the more simple shapes. They're great to work with. Both have great properties and can mimic each other in many applications. The membrane offers more flexibility because of the geometry that we can create with it.
Okay. You talked about the flexibility and some of the different properties. I know there's different ways to manufacture expanded PTFE where you can adjust maybe the machine direction orientation, traverse orientation.
Yep.
maybe radial orientation, uncintered, semi-cintered, centered, fiber length, porosity, all these parameters. I suspect that you can kind of tune these to meet the specific anatomical application.
Exactly. You know, so on a nitinol frame, for example, if you're using nitinol that's going to need to expand on its own, you want a membrane that has a lot of elasticity in that radial direction. Whether you do that with a tubing or you do it with the membrane, you don't want to hold the nitinol down. Balloon expandable, you know, it's a more controlled diameter. There's less compliance that it's going to need to see. However, it's going to need to be crimped down potentially to a lower profile. So you may need some of that Z strength or that radial strength to control those struts from poking through. And in some areas, you may want tissue ingrowth, like in a access system. You may want tissue incorporation very quickly. You may be in a structural heart area where you don't want it. So controlling that porosity becomes important as well. So you've got a lot of different inputs into the design that you can play with just with the material, which makes it a really unique material to work with.
That you talked about ingrowth. Does that ingrowth also allow for kind of anti-migration of the stent, or are there other ways that you could methods to prevent the migration of the stent between, you know, the covering and the anatomical lumen?
Sure. I mean, the ingrowth ultimately will hold it in place, but that can take weeks, if not months in some patients, to fully incorporate. So a lot of times there's going to be mechanical anchors, whether it's with exposed struts. You know, a lot of the AAA systems have anchoring to prevent them from moving because of the load the stent sees.
Okay.
To keep it in place. It does take a while for the incorporation to happen.
Okay. You talked a little bit about balloon expandable stents, and then I guess self-expanding stents are, you know, from a, I guess, is there one more popular than the other, or is it just based on application?
It's really on application. Balloon expandable stents tend to have lower profiles and tend to be smaller. The self-expanding are typically larger profiles. And you're not using a self-expanding stent for primary dilatation. Usually it's going into, it's coming in after some type of angioplasty. The path to get there is pretty clean. But people are creative. They come up with new techniques and new ideas, and it wouldn't surprise me to see some combination. Who knows what's coming next? That's the fun part of the business, is seeing what all of these customers or the physicians or the engineers come up with. And yeah, they're really creative.
Yeah. You mentioned earlier about composite stent covers. Let's talk a little bit about that in two respects. One, composites with dissimilar materials. So it might have an ePTFE and maybe some elastomeric solution, like you talked about, or even a non-woven type material. Talk to us a little bit about some of the composites using dissimilar materials, and then we'll talk about similar materials.
Yeah, so some of the composites for dissimilar materials, if I want really strong adhesion, conforming adhesion against the struts of the stent, putting layers either on the stent or using the composites on the material layers, so that it gives some type of adhesion onto the frames themselves. That's one use.
Okay.
Because ePTFE, you know, the common term is Teflon. We use it in our cooking so nothing sticks to it. So if we're going to center it onto a metal frame, we're not really sticking to the metal frame. It's how well can we encapsulate around it, or we can use some aid to help on the adhesion. We also use these dissimilar materials to as we talked about, the E and the ePTFE is this expanded porosity. Sometimes we want to close off that porosity. We want this material to actually hold pressure and not weep. And so we can use some of these materials to seal off the porosity in a very thin layer so that we still keep the flexibility and a lot of the other beneficial properties of the material and still give it a little bit more functionality, being able to seal it off.
Okay.
Another area that we use it for, ePTFE traditionally was used in vascular grafts. And one of the challenges was how do you create the anastomoses of the vascular grafts? And the ePTFE tended to not retain suture strength. The sutures would pull out if they saw tension. And so as we're putting ePTFE into more and more locations and using it in other ways, we use these composite materials to increase that suture strength so that it becomes more suturable, it becomes stronger with the sutures. And also to prevent leakage around the sutures. Because once you poke a hole through the ePTFE layer, it doesn't self-seal the way a silicone would.
Interesting. So it's some sealing properties as well. That's interesting. Okay, so moving on to similar materials, ePTFE, a fluoropolymer. Are there other composite structures that use other fluoropolymer-based materials with ePTFE?
Yeah, I think there's been some products out there where ePTFE is used with potentially PTFE, and then that PTFE could be completely unprocessed. It could be a filler material in powder form. You could also use FEP for different properties. And so those are all staying within the fluoropolymer, the fluorine side of working. And so you can keep doing all of your processing at very high temperatures. One of the things we didn't talk about with the use of the dissimilar materials is being able to, those dissimilar materials limit your temperature ranges to you work with. So if I've got to center my ePTFE, I've got to be very careful not to burn up my other materials. And so I've got to process in a way that that they can stay viable.
Right. That makes sense. Okay. I know that Medical Murray does a lot with integrating electronics, sensors, electrodes into delivery systems and devices. Have there been applications where you integrate electronics into covered stents as well?
Yes, more for monitoring. We've done some in vascular access applications, and there's always companies wanting to do monitoring of various components, whether it's blood monitoring, pressure monitoring, oxygen monitoring, whatever sensor they want to put in there. The challenge for us is they don't hold up to the centering temperatures, and so we need to go into those composite systems and work with fully centered ePTFE and somehow incorporate the sensors where we need to incorporate them so that the finished product still has all of the properties that are required. We're just working with fully centered material.
Okay, interesting. I want to just wrap things up. This has been really interesting, and we've been talking about ePTFE and some fluoropolymers in this lingering regulatory issue about PFAS. And if you think about these materials, fluoropolymer-based materials for medical device, and how they've been well received, how they're biocompatible, how many lives have been saved, the quality of life has been helped because of these materials and the devices that they're used in. We really need to get the word out about these materials. And how are you kind of handling that from a regulatory and just a customer inquiry standpoint?
It's really tough. We can't sterilize them with radiation. Radiation breaks down the fluoropolymers. And so we need EO sterilization to use them, which is an issue. The materials don't break down. They are forever chemicals. And so we just work with our customers to understand, so that they understand the issues and the benefits. If they're interested in looking at newer sterilization technologies, we'll work with them on newer sterilization technologies. We can work with, we do a lot of polyester and some fabric sewing as well. And many of the applications, at least in the structural heart, those were the materials that were traditionally used. But the ePTFE gives better performance in many cases. And it's more biocompatible. There's a lot of advantages in these applications that were traditionally for polyester and knitted products. So it's a difficult conversation because they are forever chemicals, but they have so much benefit. And you know, to your point, getting the education out there is very important. There's not a replacement for ePTFE across the board. That's just where we are. There's not a lot of sterilization, commercially viable sterilization options for ePTFE other than ethylene oxide. So they're both challenges in today's environment. Yeah, it's unfortunate, but that's where we are, and we need to continue to innovate on the sterilization side. We'll need to continue innovating on the material side. We would like to think that we're staying, if not at the forefront, at the front, at least staying up with everyone else. We're doing everything we can. But these are the best materials we have available today.
Yep. Yep. Okay. I appreciate that input. All right. Hey, Chris, this has been a real great conversation. Very interesting. And I appreciate your time.
Thanks. I enjoyed it. Anytime.
All right. Thank you.
Thank you for listening to MEDX, the Medical Extrusion Podcast, presented by US Extruders. Please subscribe to make sure you're getting the latest episodes. For video episodes, go to us-extruders.com/podcasts. All links are available in the show notes.